Okay, let us start. So our last lecture speaker for today is Professor Dmitry Melnikov. He's a professor at the International Institute of Physics in Natal. So this is like continuation of this place, which is much better. Anyways, Dmitry is a specialist, let's say, in general area of string theory, but recently he's been interested in application of knot theory, let's say, to quantum mechanics in general, but to quantum information theory. But I think his set of lectures will be exactly like interaction of knot theory with topological quantum field theory, and it's very important topic right now. So please welcome Dmitry.
Oh, thank you very much, Sasha. I think I have a microphone already. And thank you to all the organizers for organizing this school in Brasilia. It's nice to be back. Well, so this will be a set of slides, talk. So the main reason I like Blackboard talks, but the main reason that this will be about drawing, so there will be a lot of drawing, which is hard to do on the Blackboard. And as Sasha said, so the idea is to connect different areas such as knot theory or topological quantum field theory, quantum information, and maybe some basic quantum mechanics. All right, so let me just first tell about, okay, the main goals of this set of lectures is first to introduce certain correspondence between quantum mechanics and topological spaces. So when I said there will be a lot of drawing, what I meant is that I will represent different notions and concepts of quantum mechanics using spaces, topological spaces, and it will be clear what I mean a bit later. So I will introduce, this will be actually the plan of today's lecture, introduce not as much topological quantum field theories, but knot theories. So today I will talk about notions of knot theories and basics of knot theory. And finally, so I'll connect the two things, and I'll try to, as I said, express the concepts of quantum mechanics in terms of topological objects, topological spaces, and then I will try to apply this connection between quantum mechanics and topology to talk about quantum mechanics, quantum entanglement, properties of quantum entanglement, and maybe a little bit of also applications or connection to quantum gravity. Okay, this is the plan for today. I want to give an introduction to knot theory. And the plan is, if you have never learned anything about knot theory, is that by the end of this lecture, you should know how to compute Jones polynomials, at least. So that's the minimum that I suppose you learn from, in fact, the 3 lectures that I'm planning to give. Okay, yeah, that's not for today, that's for like plan for 3 lectures. So the second lecture will be about topological quantum mechanics. So it's a different way to introduce quantum mechanics using topological theories and topological spaces. And I will talk about quantum entanglement. And in the last lectures, I'll talk about applications, in particular in quantum information. Okay, so I have one more slide. This is about plan of the lecture. And as I said, there will be introduction to knot invariants and basics of knots. And I will give, well, at least there will be 2 methods of compute Jones polynomials. I'll briefly talk about other topological invariants of knots and so on. Okay, so let me start. So the first is, what is a knot? Knot mathematically is a map of a circle S1 to R3. So it's just embedding of a circle in 3-dimensional space, and there can be many different ways of doing that. And here you can see one example. This example is called figure 8 knot. So you can organize this map in such a way that lines actually form this, something which we would obviously call a knot. There's one slight generalization of the notion of a knot, which is called link. So link is just a map of several circles in R3, right? So this diagram of something which is called Borromean rings is an example of a map of 3 circles in 3-dimensional space. And here actually I'm drawing 2-dimensional diagrams, right? These are projections, but we learned, how to draw these diagrams in such a way that we can understand that these diagrams represent 3-dimensional objects. So, because in most cases, most of the time I will be working with 2-dimensional projections. So 2-dimensional projections of a knot, you can choose a 2-dimensional plane and you project this 3-dimensional object on a 2-dimensional plane. And what you need to be careful about is there will be some singular points, the intersection points. And these intersection points, in order to correctly describe the topological information, you need to specify which line goes above which, and for that we just cut one line, we just erase some piece of the line, and this indicates that the line goes beneath the other line, right? So that's actually, I will not talk much about the idea of CFT and holography, but I will mention something at the end of my lectures. So this is some kind of prototypical example of holography. You can understand this holography in a more canonical sense. You have a 3-dimensional object which you somewhat encode in 2-dimensional space in some storage which is organized in 2-dimensional way. But there is a way. So I'll reformulate it. I will tell it slightly different. So I have a 2-dimensional object, but I can use this 2-dimensional object again as this projection, as this diagram here, to actually represent something 3-dimensional. So I use some tricks here. This is just about drawing, but this is a way how I can encode 3-dimensional objects in 2 dimensions. So the canonical knot theory, right, starts from this definition of an equivalence relation. So there are many different ways of drawing a knot, but not all diagrams will correspond to different knots. So some diagrams will correspond to the same knot. And what does it mean the same, right? So the 2 knots are isotopic, which means they're equivalent if we can transform one into another without cutting diagrams. So here you have 3 diagrams, and all these 3 diagrams actually represent the same type of knots, which is this figure 8, which I showed before. And since we're talking about 2-dimensional projections, we understand what it means to transform, to smoothly deform the knot and show that we can study the relations between knots in 3 dimensions, but we want to work with 2-dimensional diagrams. So what can we do and what we cannot do to really establish the correspondence, the equivalence of knots, is formulated in this theorem of Alexander and Briggs, and also the theorem of Reidemeister in the 20s of the last century. And this consists of 3 different so-called Reidemeister moves. So if you have a pair of which tells you if you have a loop, a simple loop like this one, you can always undo this, and this costs you nothing. So this is an equivalent relation. It's an identical transformation in terms of 2-dimensional projections. You can also move one line above the other line. So this is trivial in 3 dimensions, but this is some property you need to prove the theorem in 2 dimensions. And there's another third relation, which is called the third move, which tells you can take a line and you can move it across a crossing of 2 other lines. So this is, again, if you just use these 3 transformations, you manage to map one diagram to another diagram. This means that in 3 dimensions, this diagram corresponds to 2 topological equivalent knots. Okay, so by the way, so if you have any questions, so don't hesitate to ask them at any point. So far, it is basic introduction. So here are some examples. In particular, we show that this diagram here is actually equivalent to this diagram, and so here's some set of Reidemeister moves that shows you how you can arrive from one to another. But importantly, the first diagram doesn't look very much like the last diagram, but they both represent the same, topologically the same equivalent knot. So the main problem studied by knot theory is how to classify the knots. And you can think of this as just answering the questions how many knots there are. Obviously there are infinitely many knots, but there are different infinities, so how infinite is this set of different knots? So this is one standard way of classifying the knots. So in the early days of knot theory, in the 19th century, in fact, there's an interesting physical story behind the knot theory. It started in physics, and at some point, Lord Kelvin suggested that different atoms that we observe in nature, they actually knotted vortices of ether. And well, obviously, shortly after that, it was proven that ether doesn't exist, but this idea somehow pushed some mathematics forward, and I think Tate was a mathematician, British mathematician, that started this first classification of knots. And well, this classification was actually mostly drawing diagrams. And here, for example, you can see all possible knots with up to 7 intersections. So this is the standard classification. The knot is labeled by a number of intersections. So here you start from the minimal non-trivial knot, which is called trefoil. The first one here has 3 intersections. Then there's only one with 4 intersections. This is a figure 8, which we saw before. Then there are 2. Then there are 3, and this number actually grows exponentially. So far, people, I think the first tables of Tate were up to 10 crossings, and currently, I think in 22 or about this time, 2022, there was a new paper which classified all knots and up to, I think, 25 crossings. And I think, I remember that for 16 crossings, there are about 1,300,000 something knots. So that's a pretty, well, let's say, tedious kind of work. So, I mean, okay, but I mean, people seriously do this. So the question now is, well, you have 2 diagrams, and so what you would probably want to know, this is, for example, one of the big problems for this classification. You have 2 diagrams, you draw 2 diagrams, and can you say that do these diagrams really represent the same knot, or these are 2 distinct knots? Or you can even simplify the problem and say, okay, can you tell whether these diagrams represent a trivial knot, right? The trivial knot is called unknot, is the first one in this series. It happens to be that actually, in this case, both of these are trivial knots, but I think you agree that it's not very obvious just looking at these diagrams. So how you can distinguish different knots, and even how can you tell whether the 2 knots are not trivial? So for that, what is interesting is to be able to construct a function. So given a knot, you can evaluate certain quantity, and if the quantity evaluated on 2 different things is the same, then you know that the 2 knots are equivalent or isotopic. And there are different examples of such functions, which are called topological invariants, and they can be just numbers, or some very famous cases are polynomials. So they're polynomials of some parameter here, for example, t or t and q, and they take values in complex numbers. So what you want from this function, again, so that, well, maybe it should be able to distinguish trivial knot from, so you want to distinguish your knot from a trivial knot, or maybe you can distinguish any 2 knots and links that are not equivalent. And you also want this function to be efficiently calculable. There is a number of such functions, invariants, and some of them are actually very, let's say, non-algorithmic, and they do not have algebraic expressions. For example, one very basic invariant is called tricolorability. Not all knots that they can have this property. So this is kind of function that it's a Boolean function. So it's either you can color your knot with 3 different colors, or you cannot. But this property is protected under smooth deformations of the knot. So I'll be talking mostly about invariants that have mathematical algebraic expressions, and the first one is known from the 19th century, is the Lincoln number of Gauss, and we all know it implicitly. We all use it in physics 1 or 2 course, or in electrodynamics, and it takes value in integer numbers. So after this formula of Gauss in first half of the 19th century, it took about 100 years to find another one. And it was done by Alexander. The invariant was called Alexander polynomial. It was a polynomial function, and he used some methods of homology to introduce this invariant. Well, the theory of this polynomial was later developed by Conway in 1969. So then again, there was a big gap between 1920s and 1980s. Then Jones discovered another topological invariant, which is called now Jones polynomials. And after that, it was kind of a floodgate opening, and there were a series of other polynomials, generalizations, and other different homology methods and other methods. So there's plenty of different polynomials that we know now. Well, so still, I think what is known so far, so there's certain methods like homologies, de Flory homologies, that can tell you whether a knot is a trivial knot. And there's a set of polynomials which are called Homfley-PT polynomials. So these are just initials of the mathematicians that contributed to inventing these polynomials. They are generalizations of Jones polynomials. So Jones polynomials, which I'll talk about today, they are functions of one. They're polynomials in one parameter, and Homfley, they are functions of 2 parameters. So it is believed that Homfley-PT, I think it wasn't proven, that these are powerful enough to distinguish. Actually, the colored version of this polynomial is able to distinguish any 2 distinct knots and links. So I'll move to physical examples in physics. And as I said, we know Gauss link. Well, first we know this topological invariance in certain, in electromagnetism, we learn about some wonderful topological invariants, like one of them is just the Gauss theorem, and the fact that we can compute a charge distributed in space by computing an integral over 2-dimensional surface. And if the charge is localized, then actually the result will not depend on the way we choose the surface. Another example is the Ampere's law, where we just compute the line integral of the magnetic field. And if we compute it over a closed circle, then depending on whether, then this integral called circulation computes the number of amount of current that crosses the surface, which is bounded by the circuit of the circulation. And this result, again, doesn't really depend on the choice of the circuit, of the surface. So now to the Gauss Lincoln number. So how does it appear in physics? So at the time when Gauss derived the Lincoln number, it was not yet, I think Maxwell theory hasn't yet been introduced. So we'll derive it using Maxwell theory. Well, let's take a current, let's say, which is running in some circuit gamma 1. And then we can use the Biot-Savart law to compute magnetic field using the standard formula. So here it is, this formula is, this is very physics because there is, this mu zero in the current, so it's not very mathematical yet. Then we just take this magnetic field produced with this circuit gamma 1 and insert it, well, let's choose another curve gamma 2, another circuit gamma 2, which might cross gamma 1 or not, but we will compute the line integral, the circulation of the magnetic field along this circuit gamma 2. Again, there's a lot of physics. You have still mu 0 I on one side, but then you use the Ampere's law, and as we all know, in this case, the result of this integral, as I said, should count the amount of current that crosses the surface, bounded by the gamma 2 now, right? So I write the result as, well, again, standard part, which is mu 0 times the current, and then this, well, symbol delta in this case just computes the number, well, here it's just 1 when the current crosses the surface bounded by gamma 2 and 0 when it doesn't. In fact, you can put any integer number because the current can cross the surface more than once. So in the last step, we just cancel all physics from this expression, this awful constant mu 0 and also the current, and then you get some very mathematical expression which on one side has a very terrible two-dimensional integral, and on the other side you have an integer number. So I think this should be pretty impressive, that that's such an object on the right hand side can give you something which is integer, and I'm not sure, well, okay. So yeah. Well, here's an example. I said it's plus or minus 1 because this is what we learn, let's say, in school physics, that you have a current, and usually you do just one round around this current, but you can actually gamma 1 and gamma 2, and this will appear in next examples, that you can have, for example, the same current can cross the circuit gamma 2 more than one time, and then it will not be 1 and minus 1, but it will be an integer number. So I think maybe it's not a good, it's not a very precise formula here so far. So it will be in general an integer number, right? So I should put an integer number there. I think your complaint is about this. So it's not in general 1 plus 1 or minus 1, but can be any integer number. Oh, plus and choice of the sign, of course, depends on the orientation. But the integral, of course, knows about that. Well, I mean, you need to specify your gamma 1. Oh, yeah, okay, I'm sorry. So yeah, so there's another, well, not very nice thing here. Indeed, I have this Kronecker delta with plus and minus. It's not a Kronecker delta, so it's just a notation here. Maybe not a very good notation. Okay, so again, Gauss-Linke number here appears as some, well, an integral which doesn't look, I know how to compute it directly. It's only in very symmetric cases. But the way we compute it actually, well, this is the way we learn it in physics. In school, we just measure how many times one current crosses through a loop. And so this is what we will do. So in general, to compute Gauss-Linke number, we'll just, well, first we'll choose orientation for our circuits, for gamma 1 and gamma 2, like it is shown here. And then we'll just assign, depending on the way the intersection appears in our diagram for a given link, we'll put plus 1 or minus 1. And then we'll go along the loops and count all the pluses and minuses in our diagram, sum them together, and divide the result by 2. So this will give us the result of this integral. So that's, here are some examples. The negative linking number, zero linking number, right? These are two obvious examples. Positive linking number, where we just, what happened here, well, we changed the order of intersections into cases, and that gave the opposite sign. And here, as I said, your current, for example, you can think of red as your current, and blue is your circuit that you choose. The current can go across the loop more than once, and then you can get something which is not 1 or not -1, any integer number, in fact. Okay, so so this is, I think, pretty basic at this point. I think, well, let me know if there are any questions. Okay, well, the Gauss linking number is not very powerful invariant in the sense that in many cases, for distinct configuration, it will produce the same result. In particular, these two seemingly very different configurations, very different links, give the same linking number. And the one on the right is not a trivial link, so in this case, it means that Gauss linking number is unable to resolve these two situations. But we want something that really tell us that the left side is different from the right side. And besides, this linking number is only defined on pair of circles or circuits, and it's not generalizable for more complex situation, like any link of any order with any number of components. Okay, so that was my introduction and, well, let's say physical motivation. Now I'll go a little bit to define some useful objects. I will start from the braid group, okay? So, I mean, many of you know permutation group. This is like very important group in group theory, symmetric group or group of permutations. So the braid group, if you never came across it before, it's a certain generalization of the braid group, of the symmetric or permutation group. So you can define it. It's the standard way of defining groups in mathematics in terms of generators. So you can take, well, let's say n-1 generators will define you what is called Bn braid group. So you take n-1 generators, and these generators, they need to satisfy, well, first of all, you order these generators, so they'll have labels 1, 2, 3, 4 till n-1, and then if you take two generators which are not neighbors, so the label is different by more than 1 unit, then in this case these two generators commute. Well, then they should also satisfy, if they're neighbors, that they do not commute, and they should satisfy this relation, and this relation is also called Young-Baxter equation. Okay, so symmetric group or permutation group satisfies the same relations, and maybe somebody can tell me what's the difference from symmetric group, what makes symmetric group different from this one. So for the symmetric group, there's one more relation. Does anyone remember? So it basically, repeated permutation should produce its identity operation, doesn't do anything. So this is something you relax in braid group, and this makes this group infinite. So the permutation group has finite number of elements, it's a finite group, and braid group has infinite number of generators, of elements. It has finitely generated, so there's finite number of generators, but it's an infinite group. And there is a nice way of nice representation of the braid group, and basically this representation is where the name for the group comes from, and it is defined in terms of diagrams on n lines or n strands. And well, you can think of, again, of permutation group. You have a number of objects, 1 to n, and you can permute this object. So these dots here will be these objects, these points that you'll permute, and then you just, the permutation, we'll draw this permutation. We'll start from the identity element where the result of the operation is trivial, and we do not do any permutation. And we just draw this diagram. So that's a kind of time flow for the set of endpoints. This is the identity element. And then the generators are just exchanging of two neighbors. And the first generators permute 1 and 2, the second generator permutes 2 and 3, and so on. And we'll have to define the normal generators and the inverse. And here again, the difference with the symmetric group is that we'll distinguish the two cases. So this is what symmetric group does not distinguish. So if I would draw a diagram for a symmetric group, I wouldn't care how the lines intersect each other. But here I'll have either overcrossing or undercrossing. So that's the one will be the inverse of the other. Okay, and then what's the multiplication in this group? I just put one diagram on top of the other one, so I'll just concatenate the diagrams, and the result will be again a permutation, and in this permutation I distinguish the two directions. So I either do the right twist, right flip of the two dots, or the left. Okay. And then, I mean, now you can already anticipate that this will be important for knots. So because in my diagrams, I do the same. I have two types of intersection of lines, which I want to distinguish. And in some way, I will want to use this kind of diagrams to form knots. And this was, at some point, realized by mathematicians. And a theorem was proved by Alexander, which was telling that any knot or link you can obtain by just taking a braid. So here I just put I rotated a braid 90 degrees, and then just to save the space here on the slide, I put it horizontally. So there's a braid, and then I close it in a trace-like manner. So which means I connect the inputs and outputs of the braid in a way that the lines do not intersect, and this should, for some of you at least, remind of a trace operation. So any knot or link can be constructed from a braid. Any knot or link diagram can be constructed from a braid by closing it and in a trace-like manner. So here, just an example of expression that I write in terms of generators. So U, I think in my previous slide was B. So these are just the generators B's, and I just look at this from right to left, and the same here, I construct this word from right to left. First I have U1, the inverse of the twist in the first channel, again the first channel, then the inverse in the second channel, and so on. So this is how you construct the braid, and then you can, apparently the operation here in this diagram should be computing a trace of this. Let's say if I have a group and I have a matrix representation, then it should tell me that I'm computing something like a trace. So the question is, if I do have such matrix representation of the braid and I compute the trace, will this be a topological invariant or not? Will it respect the transformation, the identical transformations on the knot, or it will not? And in fact, in general, it will not. So if you have this isotopy of the knot to be respected, you have to introduce a special trace. So this trace is known, it is called Markov trace, and it has certain properties. And these properties are the following. So let's say now it's not normal trace, it's some function. And this function should satisfy cyclicity. So if you have two braids and you multiply them, then the trace on that should be the same as the trace on the opposite way of multiplying the two braids. So this is the standard trace properties. And then there will be one non-standard one, which is called Markov property. And it is the following. So I start from certain braid, which is in the group Bn. So group Bn is in the group on n strands or n dots, And then I embed this into a larger braid group, into Bn n plus 1. And I multiply this braid by the last generator, the generator Bn, the new generator which is in Bn plus 1. So what I want for this trace to respect is the trace for this beta should be the same as in the original braid group, should be the same as beta times Bn in the larger braid group. And the reason for that actually should be quite clear if we first remember that braid group actually knows about some of the identity transformations of the knot diagrams, which are Reidemeister moves, which I introduced before. In particular, if I start drawing braids, so this is like one simple case, right? So this is my generator, and if I multiply it by another generator, the inverse of that. In terms of a braid group, this should be the result of, sorry, that's, I did the same, so I actually computed the square. So I want to multiply it by the inverse. So in braid group, this is obviously should give identity, right? So this is equal to, so here my third line is just, you know, it's a spectator. I can draw any number of lines here. What is important, just look at the first two. So this is what I showed you before, and I called it second Reidemeister move, right? Well, then you can also check that the Young-Baxter relation that for the generators that I defined before, Bn plus 1, Bn should be equal to Bn plus 1, Bn plus 1. I mean, it is a nice exercise to do it just drawing the multiplication of generators in the braid group, but this is the relation, another relation, it's a third Reidemeister move, which I introduced earlier. It tells you that you can move a line over an intersection. Well, here, this doesn't look very much like a braid, but you can arrange your lines to flow in a way that it is actually embedded in a certain braid. But there's a problem with the first Reidemeister move. So first Reidemeister move looks rather trivial, just tells you that you can unwind the loop, but braid group doesn't know naturally about this kind of relation. So this Markov property is actually intended to solve this problem. So it is intended to somehow enable you to be able to enable you to undo the loop. So how does it do this? So we'll have some. You can imagine a certain braid, and then you want to combine it with the generator. So, for example, in the way I showed on my slide. And then let's say I compute the trace. I compute the trace of this, so it means I have to close all the lines in a trace-like manner. So this requirement that the trace is the same as the trace of the original braid tells exactly that my trace should respect the first Reidemeister move. Okay? Any question here? All right. So, interestingly, that Jones, who constructed, was probably one of the first who constructed this kind of trace. I'm not sure. Maybe there are some other examples, but this is considered to be one of the most fundamental ones. Jones was able to construct this kind of trace, working with von Neumann algebras. So this has nothing to, von Neumann algebra has nothing to do with knots, at least naively, but he realized that the object that he worked with were very similar and connected to braid groups, and von Neumann algebras are just, I'm not sure this will be mentioned at this school, but these are just certain algebras of operators in quantum mechanics, certain algebras of operators that exist in quantum mechanics, and in type 2 are special in the sense that they have a special and unique trace, and Jones just realized that this trace is the, you can use this to build a topological invariant. There's another ingredient here. It turns out that important for Jones polynomials, there are certain additional relations on the braid generators, the ones that are used to compute the Jones polynomials, and they tell you the following. So if you compute and you evaluate in a topological invariant of a node diagram, then actually there are some linear relations. So if you have a diagram where you encounter some intersection like this, and you can have a very similar one which is only different in one particular intersection and has the opposite type of intersection, then you can just combine the two evaluations, the two topological invariants of these two different nodes, and then it will be equal to a third diagram where this intersection is just replaced by a pair of non-intersecting lines. And here are some coefficients. This is the way that Jones was using it in his paper. Such kind of relations were known before for the Conway polynomial, of Alexander polynomial. And here's some more detailed explanation of what this means. So you should understand this first line in terms of this being as parts of a certain specific diagram of a knot or a link. So here's a figure 8 knot. What this relation here tells you is that you can focus on one intersection and just replace it by a linear combination of well, here this, you're computing the Jones polynomial of a knot. So this relation is valid for the invariants, not for the diagrams itself. And again, you just take one specific type of intersection and you replace it by a linear combination of diagrams with two other types of intersections. Okay? And to what we see here in this example, so we started with this figure 8 knot, but the result of this operation, we have two invariants of something which is actually simpler than a trefoil knot. So the first example is actually after this change of type of the intersection, we get actually a loop. So you can use two these couple of Reidemeister moves to show that this is unknot. This is just a trivial circle. Here you get still something non-trivial, which is called Hopf-link, but you can again apply this chain relation and untie this link. So this is algorithmic procedure. At every step you will simplify the type of the knot until at some point you will just find a collection of this function j evaluated on a simple circle. And the rules here is to assign 1 to just a normal circle or any trivial knot, a knot, or so if just additional rule that you'll need to compute the Jones polynomial is if you have something knot which has two components, you have some component called k and another one which is disconnected, which is a circle. You can just take this circle and replace it by numerical expression in terms of some parameter k. K eventually will be the parameter of the invariant. Polynomial will be a function of this k. Okay? So that's again a way of simplifying the more complex case. So recursively, step by step, you can solve this relation and you can compute, reduce your calculation to just collection of simple circles, and you replace every circle by identity, and this produces your polynomial. So I'm going to walk you through one specific example. I will use a kind of nicer skein relation for this. So this kind of linear relations are also called skein relations, and I will use the version introduced by Kaufman. So this version uses a slightly different parameter a, which is standard, but is also related to the parameter q, which appeared before. And so it works like this. You have a intersection, and you just replace it by a sum of two diagrams without intersections. So you just reroute your lines in two ways so they do not intersect each other, and you multiply one by a and the other one by a in inverse. Well, you can ask, okay, there's only one type of intersection. What happens with the other one, right? So I have this, in this particular example, this is the right twist, and I told you that this is A line connected by like this, and A minus 1 line connected in the opposite way. So now, if I want, but you can ask me, what about this case? So this is the inverse. Can I simplify that? Well, what you do, you can notice that this diagram is just, if you rotate this 90 degrees in every direction, then you'll get this diagram. So what you do is just apply this 90-degree rotation to all diagrams in this relation. So then this is rotated, you get this. And the other one, when you rotate it, you'll get this. So this is the second relation. Now you can combine the two in principle and write it in the form which is similar to the form used by Jones in the previous slide. No, okay. That's an exercise. Put the coefficients correctly, and that gives you, for example, this. If you choose the coefficient appropriately here, okay? Okay, and then let's take an example of the three-fold knot. So as I said, it's just a recursive procedure. You choose first an intersection and apply this rule once. So here, just choose this one and replace it by two diagrams. In the first diagram, I replace the intersection by two vertical lines, and the second case by two horizontal lines. Then I focus on the next intersection and do the same. Now I get 4 diagrams, but actually in these 4 diagrams, well, they're still non-equivalent. But in the next step, I'll get more diagrams. But you see that now I have some. In the last 2 lines, I only have diagrams which has circles which do not intersect. And there's some small observation here. When the skein relation used by Jones, they're a little different. They also have a different normalization as compared to these ones introduced by Kaufman. And this makes the two calculations a bit distinct. So for Jones relation, you do not distinguish this situation and just a simple knot. There will be no additional factor. And for this situation, for this kind of relation, there will be an additional factor related to something like a cube or minus cube here. So you'll get an additional factor which will take into account the fact that there is loop. And this is a small bit maybe annoying property of the knots. Some of you maybe heard of that there is a thing called framing. Framing is a way you assign a normal vector to the line, to a closed line. And so there are the different topological classes of framing. And the Jones polynomial does not distinguish different classes, and the Kaufman version of this polynomial, which is called also bracket polynomial, does distinguish, but other than that, there are 2 equivalent topological invariants. Okay, any questions here? All right. Oh yeah, so that's the final result. And here, just in the last line, I show that if you get this extra factor compared to standard Jones polynomial. So the Jones polynomial will be really polynomial. Well, if you want to write in Jones variables, you have to write as a function of a to the 4th root of a. I think it's, no, okay. 4th root of q, which is a. So q is a to the 4th. So it's 1 over q here. And there will be typically a certain power of a, which is related to framing, and there will be another standard factor. Well, this is related also to the normalization of the unknot. So for mathematicians, it is nice to think of, well, normalize the knot, the unknot, just say that the Jones polynomial, the trivial one is 1. Will be kind of class of orthogonal polynomials, but it's not an orthogonal polynomial, but you start usually with 1 as the first representative. While for us it will be better to assign to a circle slightly some number. Well, I will call it D because D means dimension. Because you can think of this line as, you have an identity. When you close the line, you compute the trace of identity. So D will be dimension of your matrix, and this D is related to A in a certain way. Well, this will also appear somewhere in my slides. Okay, now I'll give you another example. So that was the first way of computing Jones polynomial. It was quite straightforward. You just do this apply recursively skein relation, and you arrive to some polynomial. We saw it in the previous example. But you can also do this using matrix representation for the braid group. So I'll construct it like this. Let's take matrix R, and this matrix R just is a matrix 4 by 4. So I just think of it as a matrix which is works on a tensor product of two-dimensional spaces, right? This is what it means. It's 4 by 4, because these two-dimensional spaces will represent lines for me, the strands of my braid. So I will start drawing braid diagrams, sometimes horizontally, sometimes vertically. So each line here is the two-dimensional space. That's a tensor product of 4 two-dimensional spaces, and this matrix R, it acts on a pair of these two two-dimensional spaces. It applies a twist. That's a diagrammatic way of thinking of what this matrix R does. It's a matrix of this exactly the same parameter A which I used in the skein relations. So now you can build the whole braid group by just tensoring this matrix R with the 2 by 2 identity matrices for one for each additional strand. So here for 4 lines, this diagram here is the generated B1. This is B1, which I obtained by taking R with 2 identity matrices. Okay, identity matrix means I have just a straight line with nothing done to it. Right? So now I can ask myself, okay, if I just compute the trace of this matrix, will it give me Jones polynomials? The answer is no. So I need to introduce Markov trace. So I'll do this in the following. I'll use this additional 2 by 2 matrix. I'll explain the notation in a little while. So this matrix 2 by 2. Well, all missing components are just obviously 0. And I'll define a trace, this trace M, the Markov trace, as just normal trace, but now with the insertion of this, this QH is 2 by 2 matrix, which means it's a matrix which is acting on just V2 on one space. So if I have n strands, I just take an nth tensor product of this QH with itself, and then I multiply by matrix X. X is my braid, and I compute the trace, and the magic here is that this will give you Jones polynomials in this Kaufman notation, okay, Kaufman's convention. So now maybe a little bit why it is called QH. So this comes from quantum groups and so on, but the idea is that this trace looks a little bit like a trace of some thermal ensemble, where Q to the H is certain, well, it's actually exponential of the Hamiltonian. So Q, you can think of some exponential of the 1 over temperature of beta, and then you compute this to the power H, and this gives you e to the minus beta h. So what I'm computing here, yeah, and okay, you have tensor product, which means that you have your Hamiltonian is the sum of a Hamiltonian for each particle, and each particle is represented by this two-dimensional vector space. You can think of a spin 1/2 Hilbert space, okay? But here's, well, there's no physics here, there's just this kind of trace will compute your topological invariance, and this will be also an exercise which I suggest you try, and it's actually quite fun. I mean, you can just put the matrix in Mathematica and then start producing any braid and compute this trace, and you'll see exactly that you produce Jones polynomials. Well, you need to do this conversion from A to Q or T to the original variables, but it works. And so this is my final rules to compute the Jones polynomial. I will normalize the regular circle in such a way that the polynomial of that is D, is not 1. Well, D will be the same factor which simplifies, which is detaches, or which eliminates this detached circle from my diagram. And finally, there will be this skein relation in the bottom line. Okay? So you can either use, now you know two ways of computing, either by skein relation. So this is just drawing diagrams. And if you have more than 4 intersections or 3 intersections, if not, you'll get tired pretty quickly, and because it will be 2 to the number of intersections, the number of diagrams we'll have to draw to compute. And with mathematical, it's a bit faster. One thing you can check, that the relation I already wrote on the board, is that D, this parameter D, which appears here, is related to A in this particular way. You can do this using, for example, the second randomized move. You can check that applying the skein relations, for example, that simplifying this diagram here, you will produce the relation between D and A. You can also compute trace of the identity matrix, the Markov trace, not the regular trace. And you'll find that, well, actually in this case it will be the same thing. You'll check that, you'll see that this is exactly minus A squared minus A minus 2. Okay, another useful object is called temporal Lieb algebra. So it's kind of an algebra for the braid group. And again, it is defined in terms of generators. I have n-1 generators, and they satisfy some relations which are not, very obvious when you look on them like this. You see that, well, there's something like Young-Baxter, but it's not Young-Baxter. Well, you have this commutativity of something which is not neighbor, and this interesting relation, if you just, obviously this U's, the generators are kind of projectors, because if you have U squared, then it's proportional to U itself. And this parameter of this algebra, again, is D, and no surprise, it will be the same D as we saw in the previous slides. And there is also a diagrammatic representation, but now diagrammatic representation without intersections. So that's, for generator, you just, instead of crossing, you just put, well, this kind of routing of lines, and U1 will just do this on the first 2 lines, U2 on the line 2 and 3, and so on. So this is the product. Well, in the product of 2 generators, you obviously will produce a circle, and in correspondence with the rules I introduced before, I'll just replace the circle by a number. So just everything which is, you can think you can just pull out of the diagram without destroying the diagram, means you can replace it by a numerical factor. So this is how you should understand the relations. Well, again, this will not really help you to understand the other ones, but you can check that they are satisfied by this diagrammatic representation. So this is an example of the temporal Lieb algebra for 3 strands, 3 dots. It is a finite algebra. It has 5. It is generated. Well, it's an algebra, right? So it's a linear space. You have this basis of 5 elements, for this particular temporal Lie algebra. So why it is useful? Well, you can use temporal Lie algebra to form braids. And if you have generators of temporal Lie algebra, and you define the parameter d in the way I told you before, then you can make a combination of identity and generators, and you can check that this particular combination satisfies the definitions of the braid group. So these BKs will satisfy Young-Baxter relation, in particular if UKs are generators of the temporal Lie algebra. But this is actually nothing but my relation, skein relation introduced before. So generator BK is kind of crossing, and then the identity operator is this parallel lines, means parallel lines I do not do anything. There is obviously some identity, kind of an identity, and then there's another element. Well, UK is the generator of the temporal Lie algebra. So you can just take the matrix representation which I introduced before, and with simple algebra, subtracting identity from the R matrix, you'll get this matrix here, and you can check that with this acting in the same way. Well, it's not here, but if you do it in the same way we did for braid generators, just take R matrix, tensor multiplied with 2 by 2 identity matrices, you can build the whole temporal Lie algebra, and you can check all the relations now in the form of matrices. So you can use this construction in particular to compute Jones polynomials, not only using Markov trace, and what I will you can, just by diagrammatic representation of the temporal Lie algebra, you can see that you can close the strands of a braid, not necessarily by closing them as a trace, but you can do this by just multiplying by the temporal Lie projectors. It's like on the right side and on the left side, I just took a certain braid, multiplied by 3 generators of the temporal Lie on one side, by 3 generators on the other side, and that produces me something. As I said, if you can pull something out of the diagram without destroying it, then it means that you just can replace this part of the diagram by a factor. So you can just replace the whole thing in the middle by this, this is called Whitehead link, and then the result will be a product of 2 generators of 2 U matrices, right? You see you have one U matrix here, one U matrix here. Well, first thing in the middle you will just replace by a numerical factor, but this is one piece of the U generator, of the pair of U generators, this is the other. Okay? I hope you can see this from the diagram. Any questions? Yeah, so this discussion is basically tied to Jones polynomials. So this way you'll get Jones polynomials. So Jones polynomials are somehow very dependent on the fact that you have the skein relation. And skein relation tells you that your representation of the braid group, the generators have at most 2 eigenvalues. So these are the matrices which have at most 2 eigenvalues. So if you try to kind of give up this relation and try to construct something more general, so supposedly you should get some more general invariants. Although I'm not sure it is easy to proceed this way. So other topological invariants, they are not based on skein relation. So in particular, you do not really have skein relation for them. And simple generalization you can actually do based on this construction. You can put 3-dimensional spaces. So 3-dimensional spaces, you should think of spin 1 particle, right? So tensor product of spin 1, spin chain of spin 1. And so in this case, you can use representation of a braid group with 3 eigenvalues. So there will be no skein relation, and I think still there will be different skein relation which you can still use to simplify, but I think you cannot do this, like next step probably won't be possible. So you'll have to do something else. So the way I just tell you, if you just replace this V2 by V3, then V4, what you'll get in principle will be called colored Jones polynomials, which what means colored? So I'll color any line with something, and this color will be actually a representation of SU2. So it's spin. Okay, so you'll get analog of Jones polynomials, but now which are called colored Jones polynomials for particles of different spin, not spin 1/2. And one more generalization, which will be important for quantum mechanics. I also want to, instead of a trace, right? Trace is only one operation I can do on matrices, and my braids are kind of matrices, which later will become some operators. So I want to also to know how to compute matrix elements. And this kind of closure of a braid, or more generally, maybe I should call it a tangle, looks like an evaluation of a matrix element, where I glue some vector on the left and another vector on the right. So it seems like I want to call this a vector right here, and this expression on the left, and this diagram on the right I also want to call a vector, which here I called phi. So how can I do this? Well, let's look at this generator of the temporal Lieb algebra. So for my convenience, I rotated by 90 degrees. So I often do this. I hope this doesn't create confusion, right? So before, actually I told you it's an identity matrix, but it's just a way of, matter of convenience of drawing this diagram. So that's U, that's the temporal Lieb generator. And so here I told you that I want to think of this as some vectors. So why not to think of this object as just product of a cat and of a bra, right? Two vectors. So where this U is a vector in this tensor product of V2 and V2. All right, so I can find a solution. So I have this matrix U, so big U, capital U. I can find this vector U. And it's a bit ambiguous. I can put some phases here also, but that's one example. So actually, to be precise, I will have a problem with Hermitian conjugation. So I want to, if I want to define the, given a cat vector, if I want a bra vector, I will not really apply Hermitian conjugation, but I will just apply the normal transposition. And I will explain why. It is just because representation, the matrix representation I'm using is not unitary. But luckily it is what is called pseudo-unitary. So pseudo-unitary, we also know this kind of representations quite well. By the way, so I'll need my A to be a phase, because if A is not a phase, then this will not work. So for phases, you have this very nice property that the conjugation is just the inverse. So phase is like a unitary number. So then, even with this property, my R dagger, the Hermitian conjugation of R of the matrix which appeared before, is not the inverse of R. But I can cure that if I introduce a matrix sigma, which is just anti-diagonal. And so if I just conjugate this R dagger additionally with this tensor products of sigma, then I'll get R inverse. And just to remind you that when we work with, well, Lorentz group doesn't have finite dimensional unitary representations. And when we write the Dirac action, and the Dirac action, we need to introduce this psi bar, right? And psi bar is not a Hermitian conjugation. It's a Hermitian conjugation multiplied by some matrix. We call it gamma 0. So gamma 0 acts like a matrix, which makes the psi bar transformed under the inverse of the Lorentz transformation. So that's kind of another version of the same thing. So then my Hermitian conjugation will actually be Hermitian conjugation and multiplication by this matrix sigma, which is equivalent to just making a transposition. Okay, so then I will have this collection. This is my vector U. This is my bra vector U. This is the tensor product of two U's and so on, right? So this is how I will build the vectors. And just to remind you, maybe U was given here. So then I'll just tensor product these vectors to build larger vectors. And from these vectors, I will just, I can, for example, this is the product of two U's, obviously, as I showed in the previous slide. If I want something like this, I just need to take U and apply a temporal leap in the middle. I have a matrix representation for that, so that will give me exactly the state on the right. Okay. So then, job's done. I will be able to compute matrix elements, and this will give me topological invariants of knots. Okay. Now switching gears. I already kind of indicated that this story has to do with quantum mechanics, and one connection was through these von Neumann algebras discovered by Jones, and shortly after, well, the other connection I just showed you in terms of matrices, and I have operators, I have matrix elements, and so on. So this is what I will use in my quantum mechanics. And shortly after the work of Jones, Witten showed that topological invariants of knots have to do something with gauge theories, in particular Chern-Simons theory. So this is the action of the Chern-Simons theory. It's kind of natural. It's a renormalizable three-dimensional gauge theory, 2 + 1 dimensional. So if you forget about the last cubic term, there will be abelian U1 Chern-Simons theory, which is just quadratic. Non-abelian theory is nonlinear. But the equations of motion of this theory are sort of trivial. So if you compute equations of motion, you'll find that the field tensor of this gauge field is just 0. So all physical configurations seem to be pure gauges, so they are not physical. And okay, so it turns out that you can still live with this, and I'll explain later. But let me just say that this kind of theories are called topological because they are metric independent, because everything which depends on the metric means it depends on distance, so we call it geometrical and not topological. So if it's metric independent, it means it's distance independent, so it only depends on shapes, not distances. So that's what we call such theory topological. So if we compute energy momentum tensor for this kind of theory, since the action is explicitly metric independent, there's no square root of G factor, the determinant of the metric, then yeah, the T menu is 0, which means the Hamiltonian is 0. So this is reflection of the fact which I just told you, that all gauge fields are all fields are just pure gauges. There are no local degrees of freedom. The theory is kind of trivial. H is equal to 0. So you can. This is one of the definitions of a topological theory. I'll give you another one next lecture. Well, but as I said, you can still do something interesting with the theory, and this means you can. Well, first you can see it by just applying gauge transformation, and if you do it naively, you'll discover that actually some gauge transformations, well, they do not change f really, right? But what they can do, they can introduce some local singularities for f, so some delta functions. And this is actually something like coupling this theory to particles. Non-dynamical particles, because I will not introduce any Lagrangian for a particle, but there will be charges, so there will be particles. And this theory has then non-trivial gauge invariant observables, which are called Wilson loops. And well, classical theory will have this gauge invariant. Well, if you open Peskin and Schroeder book, then they will tell you that this is the most general gauge invariant operators, or well, objects in the gauge theory. The Wilson loops, the traces of exponentials of the line integrals of A. And in quantum theory, you can compute expectation values, and this will be the basic correlation functions in this topological theory. So you can understand this in terms of path integral formulation, right? So you just take a path integral with insertion of this W of a non-local operator, you normalize it with something without the insertion, and this is the expectation value. So shortly after the work of Jones, Witten noticed that in SU2 theory, if you compute these objects, these Wilson line expectation values of the Wilson lines, well, Wilson line, you need to choose a contour, right, for the line, and that will compute you Jones polynomials. Well, not directly, you'll have to do some identification. In particular, this is how the parameters are related. The parameter Q, I told you that A is the fourth root of Q, and this Q is related to the coupling constant K of Chern-Simons like this. I'm not sure you can see that. Let me just write it here. So Q is exponential e to the I pi 2 pi over K pi plus 2. I hope it's larger than the slide. So the Jones polynomials in this case corresponds to the fundamental representation of SU2. As I said, it's a spin 1/2 particles. If you choose arbitrary representation, you'll get this colored Jones polynomials, as I said. And if you take SUN, you'll get something which is called Homfley PT polynomial. Okay, so I was afraid that my lecture will end earlier than expected, so I put some extra material, but I think it's good time to stop, right? And let me know if there are questions.
Okay, so first, that's this thing. So, questions, comments?
Yeah, let me just maybe briefly mention there are homework exercises, and I want to share the PDF file which has these homework exercises.
And
I think it's actually
you have to do it to get the certificate.
Certificates, yes, and it's a lot of fun. I mean, I suggest you to use scaling relation first to compute. Here I said, well, I just did it for trefoil. This is the figure 8. So try to do it for figure 8, and then use the matrix representation and show that you get the same thing. Right.
Okay, so more, not more questions.
Thank you for that. What happens when K is -2?
I heard you get gravity. Well, there are some proposals now that I haven't studied it myself, but if you just do some analytical continuation when you choose K equals to -2, but this is not very nice, right? You can see it from the formula. Well, you just add some imaginary part. I forgot, I think you put 2G Newton here or something like that. And the claim is that you get the gravity in anti-de Sitter space. I'm sorry, not de Sitter space, three-dimensional de Sitter space. So this is some analytical continuation. I told you that Q is the root of unity, so these are just phases. Q and A are phases, and this is important, so I will work with my parameter in a circle. But there are questions, what happens if you do analytical continuation to the whole complex planar, to the real line in particular. So this is an analytical continuation to the real line. So I will not talk about this, but it's certainly an interesting observation.
Thanks.
More questions?
During the construction you are doing, it seems like sometimes you are assigning orientation to the construction as a whole. Is that necessary to assign orientation or no?
Well, it was necessary to. Okay. It is not necessary for Jones polynomials for SU2. So for color Jones polynomials, and you can relate this to the fact that. Well, fundamental of SU2 is equivalent to the conjugated of SU2. So Jones polynomials in particular, so maybe I'm not sure about, I'm not right about color Jones polynomials, but for Jones polynomials, orientation is not important. But for the others, certainly for SUN, the orientation will be important. So you'll compute the topological invariance of oriented nodes and links. And this is important for a Gauss linking number also, as you saw. If you change the orientation of one of the lines, you get the negative minus sign in front.
And if you choose this as exotic gauge groups, you need to calculate for the orientable case. And what about the non-orientable case? Can I use a new machinery to do this case also, or?
You mean non-orientable groups?
Yeah.
Yeah, I mean, I think you can compute it for SO groups in particular. I guess in this case, the nodes will not be orientable as well. So, I mean, non-orientable in the sense you do not assign orientation.
More questions?
This story about orientation is somewhat important, and sometimes it helps you to correct errors in your calculations, because you may, for example, relate the orientation with the direction of the time flow and so on.
So does it make sense to define a more general knot, like to map a S1 to a general Riemannian manifold?
So I define it as S1 to R3, right? That's kind of mathematical definition. But I will work, so the Jones polynomials, by the way, so this was partially material which I skipped today. All these invariants, I will actually understand them as computed for knots in S3, the three-dimensional sphere, which is like R3, but then R3 has, you know, in a sphere at infinity, I'll just tell that the sphere is the same point, and then I'll get a three-dimensional sphere. But if you change this global topology to something different, and it will be important actually, one example is S2 cross S1 is another very simple case, very simple three-dimensional topology. The polynomials will change as well. So they're kind of labels or characteristics of these global topologies. They will know about global topologies. Usually people use more simple invariants, which are just numbers, which tell you, well, you know, there's cohomologies or homologies. These are examples of invariants. They are topological invariants, although they are groups, abelian groups, which characterize the manifold, right? You have a three-dimensional manifold, and homologies or cohomologies, they classify, they tell you which type of manifold you're considering.
Thank you.
So yeah, I will mention different three-dimensional manifolds.
More questions?
And important to mention that if you try to do this in 4 dimensions, it will not work, because in 4 dimensions you can always untie, you can use the 4th dimension to untie any knot. So knots do not exist in 4 dimensions, and this is related to the fact that we can have anyons in 2+1 dimensions, right? And not in 3+1. No, for any dimension high. Of course, everything you can do in 4, you can do also in 5 and 6 and so on.
Okay, more questions? So just very quick, this K, the level of Church-Simons is quantized here or not?
I will not really, actually in some cases I will prefer it not to be quantized. So tomorrow I will present a kind of quantum mechanical picture of this, and having K quantized will be sometimes bad. But my picture in topological invariants, Jones polynomials, they do have this natural continuation, analytical continuation to arbitrary K. Chern-Simons theory, on the other hand, is defined with, usually canonically, with integer K.
Right. Yeah. Okay. Okay, so let us thank one more time.